LEDs don't get their color from their plastic covers. The color of the light comes from the electronics themselves. The casing just helps us tell different LEDs apart. In 1962, General Electric engineer Nick Holonyak created the first visible LED. It glowed a faint red. A few years after that, engineers at Monsanto created a green LED. But for decades, all we had were those two colors. So LEDs could only be used in things like indicators, calculators, and watches. If only we could make blue, then we could mix red, green, and blue to make white and every other color, unlocking LEDs for every type of lighting in the world, from light bulbs to phones to computers to TVs to billboards. But blue was almost impossible to make. Throughout the 1960s, every big electronics company in the world raced to create the blue LED. They knew it would be worth billions. Despite the efforts of thousands of researchers, nothing worked. And the hope of ever using LEDs for light faded away. According to a director at Monsanto, these won't ever replace the kitchen light. They'd only be used in appliances, car dashboards, and stereo sets to see if the stereo was on. This might still be true today, if not for one engineer who defied the entire industry and made 3 radical breakthroughs to create the world's first blue LED. Shuji Nakamura was a researcher at a small Japanese chemical company named Nishia. They had recently expanded into the production of semiconductors to be used in the manufacture of red and green LEDs. But by the late 1980s, the semiconductor division was on its last legs. They were competing against far more established companies in a crowded market. Nakamura's lab mainly consisted of machinery he had scavenged and welded together himself. Phosphorus leaks in his lab created so many explosions that his coworkers had stopped checking in on him. By 1988, Nakamura's supervisors were so disillusioned with his research that they told him to quit. So it was out of desperation that he brought a radical proposal to the company's founder and president, Nobuo Ogawa. The elusive blue LED. What if Nishia could be the one to create it? Ogawa took a gamble. He devoted 500 million yen, or $3 million, likely around 15% of the company's annual profit, to Nakamura's moonshot project. By the 1980s, after hundreds of millions of dollars had been spent hunting for the right material, every electronics company had come up empty-handed. But researchers had at least figured out the first critical requirement: high-quality crystal. No matter what material you used for the blue LED, it required a near-perfect crystal structure. Any defects in the crystal lattice disrupt the flow of electrons, so instead of emitting their energy as visible light, it is instead dissipated as heat. So the first step in Nakamura's proposal to Ogawa was to disappear to Florida. He knew an old colleague there whose lab was beginning to use a new crystal-making technology called metal organic chemical vapor deposition, or MOCVD. An MOCVD reactor, essentially a giant oven, was and still is the best way to mass-produce clean crystal. It works by injecting vapor molecules of your crystal into a hot chamber, where they react with a base material called a substrate to form layers. Nakamura joined the lab for a year to master MOCVD, but his time there was miserable. He wasn't allowed to use the working MOCVD, so he spent 10 of his 12 months assembling a new system almost from scratch. He returned to Japan in 1989 with an order for a brand new MOCVD reactor for Nishia. But now the question was, with MOCVD under his belt, which material should he research? By this time, scientists had narrowed the options down to 2 main candidates: zinc selenide and gallium nitride. These were both semiconductors with band gaps theoretically in the blue light range. Between the 2 candidates, almost all researchers were focused on zinc selenide. Nakamura surveyed the crowded field and decided that if he were going to publish 5 papers by himself, he'd better focus on gallium nitride, where the competition was much less fierce. When Nakamura attended the biggest applied physics conference in Japan, the talks on zinc selenide had over 500 attendees. The talks on gallium nitride had 5. 2 of those 5 attendees were the world experts on gallium nitride, Dr. Isamu Okazaki and his former grad student, Dr. Hiroshi Amano. A few years earlier, they had made a breakthrough on the first problem of high-quality crystal. Instead of growing gallium nitride directly on sapphire, they first grew a buffer layer of aluminum nitride. This has a lattice spacing in between that of the other two materials, making it easier to grow a clean gallium nitride crystal on top. The only issue was that the aluminum caused problems for the MOCVD reactor, making the process hard to scale. But Nakamura wasn't even close at this stage. Back at Nishia, he couldn't get gallium nitride to even grow normally in his new MOCVD reactor. After 6 months, desperate for results, he decided to take the machine apart and build a better version himself. His 10 months spent putting together the reactor in Florida were suddenly invaluable. After a year and a half of continuous work, he came into the lab on a winter day in late 1990. As usual, he tinkered around in the morning, grew a gallium nitride sample in the afternoon, and tested it. But this time, the electron mobility was 4 times higher than any gallium nitride ever grown directly on sapphire. Nakamura called it the most exciting day of his life. His trick was to add a second nozzle to the MOCVD reactor. The gallium nitride reactant gases had been rising in the hot chamber, mixing in the air to form a powdery waste. But the second nozzle released a downward stream of inert gas, pinning the first flow to the substrate to form a uniform crystal. For years, scientists had avoided adding a second stream to MOCVD because they thought it would only introduce more turbulence. But Nakamura used a special nozzle so that even when the streams combined, they remained laminar. He called his invention the two-flow reactor. Now he was ready to take on Akazaki and Amano. But instead of copying their aluminum nitride buffer layer, his two-flow design allowed him to make gallium nitride so smooth and stable, it itself could be used as a buffer layer on the sapphire substrate. This, in turn, yielded an even cleaner crystal of gallium nitride on top, without the issues of aluminum. Nakamura now had the highest quality gallium nitride crystals ever made. With crystal formation settled, he turned to the second obstacle, creating P-type gallium nitride. Here, Akazaki and Amano had again beaten him to the punch. They had created a gallium nitride sample doped with magnesium, but at first it didn't perform as a P-type as they expected. However, after exposing it to an electron beam, it did behave as a P-type, the world's first P-type gallium nitride after 20 years of trying. The catch was that no one knew why it worked, and the process of irradiating each crystal with electrons was too slow for commercial production. At first, Nakamura copied Akazaki and Amano's approach, but he suspected the beam of electrons was overkill. Maybe all the crystal needed was energy. So he tried heating magnesium-doped gallium nitride to 400 degrees Celsius in a process known as annealing. The result? A completely P-type sample. This worked even better than the shallow electron beam, which only made the surfaces of the samples P-type. And simply heating things up was a quick, scalable process. His work also revealed why the P-type had been so difficult. To make gallium nitride with MOCVD, you supply the nitrogen from ammonia. But ammonia also contains hydrogen. Where there should have been holes in the magnesium-doped gallium nitride, these hydrogen atoms were sneaking in and bonding with the magnesium, plugging all the holes. Adding energy to the system released the hydrogen from the material, freeing up the holes again. By now, Nakamura had all the ingredients to make a prototype blue LED, and he presented it at a workshop in St. Louis in 1992 and received a standing ovation. He was beginning to make a name for himself. But even though he had created the best prototype to date, it was more of a blue-violet color and still extremely inefficient, with a light output power of just 42 microwatts, well below the 1000 microwatt threshold for practical use. At this point, he only had the third hurdle left, getting his blue LED to a light output power of 1000 microwatts. A known trick to increase the efficiency of LEDs was to create a well, a thin layer of material at the PN junction called an active layer, that shrinks the band gap just a bit. This encourages more electrons to fall from the N-type conduction band into holes in the P-type valence band. The best active layer for gallium nitride was already known to be indium gallium nitride, which would not only make the band gap easier to cross, but also narrow it just the right amount to bring its blue-violet gap down to true blue. Nakamura had an advantage: his ability to customize his MOCVD reactor. This allowed him to use brute force, adjusting the reactor to pump as much indium as he could onto the gallium nitride in the hopes that at least some would stick. To his surprise, the technique worked, giving him a clean indium gallium nitride crystal. He quickly incorporated this active layer into his LED, but the well worked a little too well and overflowed with electrons, leaking them back into the gallium nitride layers. Unfazed, within a few months, Nakamura had fixed this too, by creating the opposite of a well, a hill. He returned to his reactor one more time to make aluminum gallium nitride, a compound with a larger band gap that could block electrons from escaping the well once inside. The structure of the blue LED had become far more complex than anyone could have imagined. But it was complete. After 30 years of searching by countless scientists, Nakamura had done it. He had created a glorious bright blue LED that could even be seen in daylight. It had a light output power of 1,500 microwatts and emitted a perfect blue at exactly 450 nanometers. It was over 100 times brighter than the previous pseudo-blue LEDs on the market. Nakamura wrote, "I felt like I had reached the top of Mount Fuji." Nishia called a press conference in Tokyo to announce the world's first true blue LED. The electronics industry was stunned. In 1996, they made the jump from blue to white by placing a yellow phosphor over the LED. This chemical absorbs the blue photons and re-radiates them in a broad spectrum across the visible range. Soon enough, Nishia was selling the world's first white LED, at last unlocking the final frontier so many had doubted: LED lighting.